Okay, welcome to part two of the story of the discovery of the Big Bang. The idea, the theory, the founded on solid evidence that the universe, 12.6 billion years ago, or give or take a few billion, had a beginning, right? It was all compressed. It's a crazy idea, but it's real. It's real science, and there's good reason to think it's true. Okay, so I want to go back in time now to understand this concept. There's a guy named Doppler, and you might have heard of Doppler radar or whatever. Well, this guy here, he didn't invent Doppler radar. It's named after him, right? But Christian Doppler, if it's white, you got to write that down. And we're talking 1803 to 1853. So he, became 50 years old before he passed away. And the point is, again, dates. I'm not super. I don't think it's really super duper important to memorize particular dates. It's nice to know it, but picture this was before the Civil War. Okay, he lived in Europe, so he didn't live in America. But if you want to place it in your sense of history, it was 1776 was the Revolution, 1865 was the Civil War. So in that time period between the American Revolution and the Civil War, okay, and that's I don't know how much you know about history, but that would be the block of time he lived during. Now he made a discovery that's actually pretty cool. He didn't study light, although his ideas became used with light later. He was studying sound and acoustics. And you may have noticed that think about what does it sound like if, let's say, a car goes driving by, or especially if it's honking the horn, or a race car. Now, I'm not talking about the gear shifting. That's the gear shifting. That's not what I'm talking about. I'm talking about when it drives by, when it's coming toward you and goes by, there's a change in the sound as it passes you. It starts out high pitched and then it changes right as it passes you to lower pitch. It's like, meow. You see what did you hear? Did that sound familiar? Okay. What I'm doing is lowering the pitch of my voice to make that sound. Or let's say an ambulance comes by. It's like, nee, 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 nee. Or a train, coming by. Ding, 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 with the bell. And so that particular change of pitch, he was wondering, what's going on with that? Why does it do that, right? He was a physicist and acoustician who was studying acoustics. And so he's the guy who figured out how that works and why it works, okay? Christian Doppler, and it became called the Doppler effect, okay? And so I'm going to explain how it works in a minute. Try to keep that question in your head. Why would this? Do you know what I'm talking about, though? Do it for yourself. Make the sound of a car or something going past you. And notice your voice drops to imitate that sound. It's a change in the pitch, which, by the way, high frequency, high notes, right? They have a short wavelength, just like light, right? And low frequencies have longer wavelength, just like red and light. Okay, so anyway, that's a little bit of a hint. But the idea here then is he discovered this thing called the Doppler effect, okay? And so here's kind of a picture of it. And what's going on here? It's a little tricky to understand. But notice the circle is around where the ambulance is now, right? Notice this circle is around where the ambulance was when it gave off that wave. This circle is centered where it was when it gave off that wave. The idea is as it gets closer, the waves will compress, okay? And as it goes away, the waves will stretch out because it's moving in relation to you. As it's coming toward you, as it gives off a wavelength in all directions, before the next wave comes out, it moves a little bit toward you. So it's a little closer, right? And the next time the wave goes out, it moves a little bit toward you. So the waves are closer. The idea is as it's moving forward, it's kind of catching up with these waves. So they would be less distance between them. And it's kind of moving away from these waves. So there's greater distance between them. This would have a longer wavelength. This would have a shorter. So as it goes by, well, let me get the direction right. It goes, right? As it's going toward the listener, then it sounds high pitch. As it's moving away from the listener, it's a lower pitch, okay? So that's called the Doppler effect. Shorter wavelength, higher frequency as it's moving toward you. Longer wavelength, lower frequency if it's moving away from you. So you could tell by the pitch of the sound that whether something's coming toward you or not. If you know what the sound is, originally, you could tell whether it's moving toward you or away from you. Now, how he came up with this is actually kind of a cool thing. What the experiments Doppler did to discover how this works. All right. Now, that period of time he lived in, there were these new inventions called trains, choo-choo trains. And this was the Industrial Revolution, right? And suddenly with the invention of the trains, they put them on tracks. You know, at one point in time, people thought, wow, there's a certain speed you can't move because it'll suck the breath out of you and you'll suffocate. Well, that didn't happen. But people could suddenly move faster than they'd ever moved before. Before there were trains, I mean, you could go on a boat. Well, it could just move around kind of slowly down the river or whatever. Or you could you could run, or you could ride on horseback. Now, nobody's ever been on horseback and you hear like so fast it goes like clip, clop, clip, clop, clip, clop, clip, clop, clip, clop. That doesn't happen, right? But the train, they started noticing that the whistle goes meh, meow. So what he did is he hired somebody to play a middle C note on a trumpet, to be on the train playing that note. And he had on the side of the track with him another guy playing a middle C note. And he could tell as the train was coming toward you, it was higher pitch than the middle C that the trumpet player was playing next to you, stationary. And it was lower pitch when it was moving away from you. So he did it by comparing trumpet players. But here's the thing too. The same exact effect happens whether you're on the side of the track or whether you're on the train. So if he was on the train going by the guy playing the middle C on the trumpet, he would hear the pitch of the note being played is a higher pitch when he's approaching the guy on the side of the track, and lower. So it sounds like meow. Whether you're on the train listening to one on the side of the track, or whether you're on the side of the track listening to one on the train, right? Either way, if the thing is moving toward you, which would be whether you're moving or it's moving, if you're coming together, it will blue shift or it will make a smaller wavelength. And if it's moving away from you, it makes a longer wavelength. Okay, that's the key thing to remember on that. All right, so this concept of the Doppler effect, he came up with it in terms of acoustics. And later, scientists realized the same thing would happen with light. And we'll get to, and we'll get to that in the next segment.